Here's an example. Let's look at some data here. This is rates of crime, I believe, per 100,000 in different states of the U.S. So we have rates of arrests per 100,000 residents from the 50 states, including the District of Columbia. And I should note that, let's take a look at this. I do have some slides, so rather than forgetting about them, here's probably more information that you really wanted to know about K-means, which is what we're looking at now. Explained as simply as I can based on what I understand. You're trying to minimize the within-group sums of squares based on group membership of the points and whatever the objective criterion or distance measure is. Okay, so that's really what you're doing. We have all these scary-looking equations, but essentially that's what it boils down to. You want to minimize the within-group sums of squares over all of the variables. Now, if you're a statistical genius, and that leaves me out for sure, you will quickly realize that if you have even a fairly decently sized set, in order to, there's not a computer big enough in the world to exhaustively examine all of the solutions in a brute force method. It's too big. And in fact, K-means clustering is sometimes called hill climbing. It's a hill climbing simulation or optimization algorithm. And what that means is you might end up at an optimized solution, but it might be a locally optimized solution, such that if you had split up the data into different segments to begin with, you might have headed off in a completely different direction. So that's one of the intractable problems with K-means clustering. You're not assured of having the very best definitive solution ever. So to address that, a lot of the people recommend that you do it several times. If you're focused on group membership, if let's say you're trying to use K-means to get the optimal membership at the individual observation level for the three groups, you should probably run it several times at least and take a look at how the group membership differs. Okay, so another issue is scaling. And the scaling issue is not unique to cluster analysis. Of course, we're talking about so-called multivariate data, and what multivariate means is that they're correlated. They're related to each other, but not in a deterministic modeling point of view where you have a predicted Y variable and then you have X variables. It's not like that. We just have columns of numeric data, and it usually always has to be numeric for cluster analysis, but they need to be on the same scales. If they're on different scales, you've got to fix that because it will have a major impact on the whole process. Now, scaling does not necessarily mean standardization, although that's usually the most common approach. Is you take the values for every column, every variable, and you mean center them. You subtract the mean for that column from each observation, and then you divide by the standard deviation, and that gives you a z-score. It gives you something that's sometimes called a walled statistic. You get a z-score that will range from minus 3.5 to plus 3.5. But you don't have to do that. You can also standardize based on range. Just take the range of the columns and make them all fit within some sort of standard range. And there are other approaches as well. Okay, so this is what we're going to do with the crime data. These are the categories of crime, and we're going to produce a scatter plot matrix, which is a good idea just to kind of get a feel for the relationships among all of the bivariate relationships, all of the pairs of variables. Also, a scatter plot matrix can help you spot outliers. Outliers is a third problem, a third intractable problem with K-means. Outliers can really throw a monkey wrench in the works. So if you have one or two, you need to get rid of it. And this is an overview of what we're trying to achieve. This is, if we look at and we'll do this with R, we will compute a 2-group, a 3-group, a 4-group, a 5-group, and a 6-group solution. And with each of those different solutions, different segments, a two-segment solution is different from 3, different from 4. We'll calculate the reduction in the within groups sums of squares. And what you look for, and this is just a heuristic, you look for the elbow of the curve. The best solution is usually the one where the drop in the within group sums of squares is the biggest, which would imply either here for this one or maybe here, probably 2. A 2-group solution looks the best. Okay, so give you a heads up, and then we'll do some other graphical checking. We'll check our solution by plotting the group membership on the basis of the first and second principal components, which is a common technique to take a look at group membership, whether you have 2 groups or 3 groups. The reason is the first 2 principal components usually explain well over 90% of the variance, and sometimes even more than that. They explain most of the variance in the data. So if you're going to use two dimensions, 2 orthogonal dimensions, which is what a matrix scatter plot is, orthogonal, they're at right angles from each other, the scores of the first principal components are good choices because they account for the lion's share of the variance in the data set. Okay, so this is just another visual approach, which is just kind of a check on your solution. There's no cookbook. There's no recipe that will lead you to the very best solution. So anyway, let's take a look at that, and then we'll come back to model-based clustering. Okay, so here's our data, and we're going to create it. So, and we'll just do that really fast. We'll roll it up into a data frame, and then we can take a look at it. We'll pop it open here. And so it's just 51. Not sure why they're 51. I thought we had 50 states. Looks like they're 51. Here, the row names are the states, and then these are we're going to cluster based on these 7 variables, which are the arrest rates for these various types of crimes. Okay, so there's our data, and then it doesn't matter. We can put it in a data frame, and we did. And so the next thing we're going to do is we're going to do the scatter plot matrix. So let me give this a little real estate. And when we do that, these points are kind of small for you to see. But the objective of doing the scatter plot matrix is first to look at the bivariate relationships, and most of them are very clearly positively correlated, which you would expect. If you have people getting arrested for robbery and at some level, it just intuitively makes sense that the arrests for assault might have a similar trend, and they do. What about the outliers?